outline here was only about 9 lines long. And most of this, it's a basic concept. You have an experiment which takes up a page and a half. You have an example which takes up a page and a half. There's only 5 pages of reading, which meant you actually had to read about a page and a half. Okay, so that's why the notes are so short for this section. The 2 basic concepts in here is the fact that when a reaction occurs, that there is a heat transfer that takes place many times. I'm going to say many times there is a heat transfer that takes place. Sometimes it's so negligible that you have to use some pretty precise measurements in order to determine it. In some cases, the heat exchange is pretty dramatic. And rather than doing the experiment, which is basically I put some drain cleaner and pour some water in it, it heats up and you can hold it and feel that it's warm. You're all comfortable that you can visualize that happening. We don't have to actually do that. But especially with so many athletes in here, you've probably had cold packs and heat packs before. The example they use in here, figure 10.7 on page 362, shows a cold pack. So if you sustained an injury in a game and the coach or the manager takes out this pack, they usually pop it or they press it and pop it and they rub it together and then they put it on you and it's nice and cold. That is because there's a reaction that's taking place in there where the heat transfer is pretty dramatic. In the same way here they show this warm pack, often used by hunters for their boots and their hands, or maybe fishermen. They go ahead and pop these, and in the same way that the cold pack chills, here the heat pack warms. And so they have a source of transferable, transportable heat. So when you're in that duck blind or ice fishing, which I love ice fishermen here, right? Ice fishermen? No? Okay. It happens. People do that. They go out on a frozen lake, drill a hole, drop a line, and tempt the fish, who are alive underneath because of hydrogen bonding, right? Because all the ice is at the top. See, it's chemistry. It all comes back. Okay, so a reaction is taking place, and there is an energy transfer, which is causing there to be a temperature change. The 2 different definitions we had to learn for today, or maybe relearn or be re-exposed to, are the terms exothermic and endothermic. Okay? And the terms exo and endo refer to which direction the heat is moving, which direction the temperature change is occurring. Heat is energy, and we'll talk more specifically about that in a later chapter. But energy is being transferred either out of the reaction or into the reaction. And by, let's say we're holding the beaker with the reaction taking place in, we're going to feel a temperature change. That temperature change is being produced by the transfer of heat either into or out of the reaction. So the key here is knowing the 2 prefixes, right? They're both thermic. The term thermic means dealing with therms or dealing with temperature. Temperature is related to heat. Okay, so it's either endothermic or exothermic. And if you can remember one of them, the other is the opposite. So 2 terms, memorize one, knowing the other is the antithesis, or the opposite of that. Exo and endo. So, have you ever heard the term exo before? Okay? Give me an example of the term exo. Where have you heard exo from? That's exactly the phrase I was thinking. I heard over here first, exoskeleton. Where have you heard that kind of a phrase or idea from? An exoskeleton. Biology, okay. Or maybe science fiction movies, or maybe gaming. Okay. What does it mean if something has an exoskeleton? All the hard parts are outside, right? Outside. Over top of the doors. And many, not in the room, but in the building. Like when you go in the hall and you want to leave the building, what do you look for? What kind of a sign? Exit sign. Exit means to leave, to go out. Okay? An endoskeleton or exoskeleton. In the case of an exoskeleton, the hard parts are on the outside. Basically, the insect has body armor. And the body armor for it on the outside is similar to us with our bones on the inside. You might say that we have an inside skeleton, they have an outside skeleton called an exoskeleton. When you're in the building and you want to leave, you look for the exit signs to go out. So keep that idea in mind. With exothermic means the heat is going out. It's exiting. If I hold something in my hand and it's reacting and it's an exothermic reaction, heat is going out of the reaction. Where is the heat going into? My hand. Because heat is going out of the reaction and into my hand, what is the sensation that I have? Hot. Okay. An exothermic reaction is giving off heat, so it's hot. It feels hot to me. My hand is receiving the energy that the reaction is giving off in an exothermic reaction. So if you can remember, exothermic is to exit. Exothermic means for the heat to come out. When it comes out of the reaction, it goes into my hands. Feels warm. The opposite of that is endo. Endo is energy coming out of the environment into the reaction. The reaction is a heat sucker. It's drawing energy into it from the outside. You think of it that way, if we had signs over the doors on the outside of the building where it's exit to go out, it would be some kind of endo to come in. Entrance, right? Entrance, endo, exit, exo. So just think of it that way. To enter something is endo, means something's coming into it. What's coming into it? The energy. Energy is coming into the reaction. In my hands, if energy is needed, think of it that way. The reaction takes place, and the reaction is going to draw, it's going to suck in the energy from around it. It's going to suck in the heat around it, and that's the energy form. If I have it in my hand, and energy is going into the reaction, it's coming out of somewhere. It's coming out of my hands. When the energy is coming out of my hands, what's the sensation that I get? It's cold. So looking down at these two tacks here in figure 10.7, on the cold tack, when I hold a cold tack that's been activated, it feels cold. Because it feels cold, where is the energy? Is it coming out of it or into it? Energy is going into it because it's coming out of my hands. That's why it feels cold. Because it's taking my energy. The energy is going into the reaction. So what kind of reaction is taking place? Energy is entering the reaction, right? It's entering. It's an endothermic reaction. On the right is the heat pack, the antithesis. In my hands, it feels hot. It feels hot because energy is coming out of the reaction and into my hands. Since the energy is coming out of the reaction, it feels hot to me. The energy is coming out. It's an exothermic reaction. Energy is exiting the reaction. Okay. Endothermic absorbs heat. Exothermic gives off heat. Heat exits in an exo. Heat enters in an endo. There, we're done. Oh, we'll do the stoichiometry too, but that is basically all that's there in the thermic portion, right? In the section that deals with energy changes that occur, I have the definitions of exo and endo. I have how exothermics increase the surrounding temperature and endos decrease the surrounding temperature. Most solids dissolve, it says this in the text. Most solids dissolve in what way? Most solids dissolve endothermically. Okay. Which really means they react endothermically. So when they're dissolving, that they're taking energy into the reaction, they're making everything else feel colder. So they made the point the other day when we made that supersaturated salt solution, that in my hand, if I put the salt in, it would have been endothermic. That dissolving process would have been endothermic. Well, think about it. In order for the solid to dissolve, more energy had to come in because we're trying to make separation, right? When we're making the separation, energy's coming in. To make that happen, where's the energy come from? It has to come from somewhere. It doesn't come out of nowhere. If you can figure out how to harness that energy from nowhere, you'll make your billions of dollars, okay? But as the energy goes into the solution, it has to come from somewhere. It comes out of my hand. It's drawing heat in. It should have felt cool in my hand. But again, it was such a small amount that I wouldn't even notice it. But we can set up a very technical, not even that technical, but we can set up an experiment where we can actually measure the energy that's gained or lost. And actually, we're going to do that in a later module. I believe it's the later module. We're going to do that. Oh, by the way, that later doing of the measuring of the heat transfer is chapter 2 in the old book. If you imagine chemistry doing that as your second week after doing significant figures, precision, all that. Okay, so that's why I like this teaching order better. When you get to heat transfer, you kind of have an idea of what's taking place, rather than just learn it, just accept it, and then later on in the book be able to apply it. There's other things where there's a trade-off too. The other book had strengths too, but you got to pick one or the other. And I think this order makes a lot more sense. Let's go ahead and move on then to this idea of applying stoichiometry to solutions. And it's really only a page and a half with one example and like one paragraph of content. So all my notes for this whole section is see the example. It's really all it is. Okay? And it's a chance for us to go back and refresh what we did last module, doing our H solution diagramming and everything. But I assume that there are problems like this in the homework. You go ahead and flip ahead to the practice problems where you are applying stoichiometry to it. I mean, other than the ones for tomorrow, I've already done those. There's only 3 of them, I believe, that we're doing for tomorrow. So let's go ahead and you can write these in your notes. I'm going to do example 10.1. We're going to work through that, both part A and part B. Okay? Now again, they're done right in front of you, but they're not done exactly in the same order, in the same manner that I've taught you. What I'm going to teach you, or what we're going to review, because since we've already taught it, is using the H diagram as your solution pathway. Remember, that is not anything other than a graphical way of representing all of these conversion factors that they use. And I might want to warn you that in the on your owns, that there is an on your own, there's an error in the key. So let me go ahead and give that to you now as well. If you flip back to page 376, you'll notice in the middle, dealing with question 10.5, that it gives you the stoichiometric relationship of 2 to 2 moles of NaOH to 2 moles of aluminum, and that is correct. However, how many moles of aluminum do they indicate were in that sample? Notice there it says there are 44 moles. Do you see that in the middle of page 376? There are no yeses and no nos. So the net is what? Just some feedback. Do you see what I'm talking about? In the middle of page 376, on the answer solution for question 10.5, in the third formula row, it says 44 moles of aluminum over 1 times 2 moles of NaOH over 2 moles of aluminum equals 44 moles of NaOH. Do you see that? Replace 44 with 55. Okay, so you have a different addition. There are two printings of the same addition that are in circulation. So some of you have the updated one. Mine says 44 moles of aluminum instead of 55.5 moles. It should be 55.5. So if you have the same printing as I do, you need to make sure you make that correction. Because you'll get there and go, where did 44 come from? Okay. Just so you don't think I'm totally crazy. See where it says 44? And I change it to 55? Okay, 55. All right. So since you do have the answer keys to do on your own, I would hate for you to sit back there and go, chemistry is so hard, I have no idea where 44 came from. In your print, it's a typo. Example 10.1. A chemist wishes to make calcium carbonate by using the following reaction. I dropped the phase symbols, but know that these are aqueous, except for the calcium carbonate, which comes out as a solid. That's why you can use it in Tums. You don't get a gel cap, you get a solid Tums capsule. It's solid. The calcium carbonate is what we're looking for. So it says if the chemist mixes 15 milliliters of 1.23 molar sodium carbonate. So I know I'm dealing with this molecule here in the reaction. So we draw my vertical line. With excess calcium hydroxide, how many grams of calcium carbonate will be produced? So again, I write the formula down, and then I go through and I'm going to put the vertical line under the molecules that are in question that I'm actually going to be assessing. The question said how many grams of calcium carbonate. What other information have I been given? Well, if I draw my horizontal line, my stoichiometric relationship is going to be a 1-to-1. Okay. I've been given that it's 50 milliliters and 0.050 liters of a 1.23 molar solution, and I want to get to grams. I'm going to move from my known to my unknown, right? Where's my solution pathway going to take me? Up, over, and up. I know that this times this will give me my number of moles here. This to this relates to my number of moles, so it's 1-to-1. It's going to be the same thing over there. And then I need to somehow go from here to here, and I'm going to do that by multiplying by what? The molar mass. Okay. So I know everything I need to get there, and I can figure out everything I need. Let's just move along the pathway. This times this, do I have both parts? Yes, I do. So how many moles am I looking at? 0.0615. So when I have 50.05 liters, or 50 milliliters, of a 1.23 molar solution, in solution I have 0.0615 moles of sodium carbonate. And because they're related 1-to-1 stoichiometrically, I also then know that I can produce 0.0615 moles of calcium carbonate. And because it has a molar mass of 100.1 grams per mole, I know that my number of moles times my molar mass is going to give me 6.16 grams of calcium carbonate. Now, I did that kind of rapidly, but this is, again, review from last module. I was given this and this so I can compute this. From here to here, I use stoichiometry coefficients. From here to here, I need to go and multiply by molar mass to get mass. So when I react 50 milliliters of a 1.23 molar sodium carbonate, I'm reacting 0.0615 moles of sodium carbonate. And if I have excess calcium hydroxide, it will produce the same number of moles of calcium carbonate. That number of moles of calcium carbonate at 100.1 grams per mole will have a mass of 6.16 grams. Clear as mud? That is the first half of the example problem. Now notice if you followed it in the text, doing it completely by just knowing the conversion factors, they first convert 50 milliliters into 0.500 liters. Then they use the relationship of 1.23 moles per liter. It's going to give you that number of moles. Stoichiometry, this times 1/1 gives you this. And then this times this over 1 gives you this. So they walk you through. All the math is there. It's just, how do you know the process? The thing I like about the solution diagram is that your process is visual right in front of you. I'm going from here. I end up there. How do I get there? I can't just kind of go, woo! I don't understand how I got the answer. Okay. Step 1 times step 2 brings you step 3. Step 3 times this here gives you 4. This times this gives you this. Why is it this times this? We're going up. If I were over here working this way, what would my processes be? From here to here would be division. From here to here, division. Now on the text, it's going to look like multiplication, but it's going to be inverted. Remember, to divide by something is to multiply by the reciprocal. As a matter of fact, in this one, the second one, we do just that. We move from a mass, and we're going to move back over here towards a volume. So let's look at the second half of example 10.1. Erase the Candyland root over here. Start calling Candyland chemistry. I got an answer, but I have no idea how I got it. You follow the path to Candyland. The second one. How many liters? Okay, well, they give the reaction below. Let me go ahead and write the reaction up first. You've got 3 sodium chloride and aluminum nitrate. React to produce aluminum chloride and 3 sodium nitrate. Okay. The question says, how many liters of submolar sodium chloride, so we're going to be dealing with this, will be necessary to make 100 grams of that. So these are the 2 molecules in question. It said we had a 0.25 molar solution of sodium chloride. And the question ends with how many liters of that. So going from my known to my unknown, given this, how much of this? So my pathway is going to be down, across, and down. If I have 100 grams of aluminum chloride, how many moles of aluminum chloride do I have? Remember, because your moles are going to reside, your answer's going to be right in here. How many moles do you have? Don't know yet, but we can find it out by doing what? Dividing by the molar mass. And the molar mass here, I would add 1 aluminum. Aluminum is basically 27, and 3 chlorines, which are 35.5 each. And I have that I would get 133.5. Is that right? 133.5 grams per mole. So 100 divided by 133.5 gives me 0.749. Is that right? Mm-hmm. When I have 100 grams, another way of saying that is I have 0.749 moles of aluminum chloride. It's a metal and non-metal, that's why it's not aluminum trichloride, right? It's covalent to be a trichloride, but it's not, it's ionic. The mass times, or excuse me, divided by the molar mass gives me this number of moles. My next stop on the pathway is this part over here, this side over here. How do we get there? Well, stoichiometry says that it's a 3-to-1 relationship. So moving in this direction, I multiply by 3. Everybody see how I get that, right? If you don't, talk to me after class. This should be like, oh, I'm so bored of this. This is old stuff. But this number of moles, since it's 3-to-1, I multiply by 3, and I end up with 2.247. What have I just said? When I have a reaction that produces 0.749 moles, I have to react 2.247 moles of this. Why? For every 3 moles of this, I only produce 1 mole of this. So now I'm working it backwards. So given this, I need 3 times as much of that to react. So at this point now, I'm my solution pathway. How do we get the liters? Well, remember this. Molarity is equal to the number of moles divided by the number of liters, right? In the same way, liters then is equal to the molarity, the number of liters is equal to the number of moles divided by the molarity. See, that's exactly what we have here. Moles divided by molarity. Moles divided by molarity gives us liters. So 2.247 divided by 0.245 gives us 9.17 liters. So I need 9.17 liters of a 0.245 molar solution of sodium chloride. And when I react that with enough aluminum nitrate, it will produce 0.749 moles of aluminum chloride, which will have a mass of 100 grams. Let's look to the on your own for 10.4 and 10.5. This is all example 10.1. Okay, so you have all this math. It might look a little different because rather than dividing, you may have see it say multiply by the reciprocal. Multiplying by the reciprocal is the same as dividing. Just as you follow through the book. Now, I'm going to introduce you to a little bit of shorthand. And I do this only for time savings. But for problems like this, when I know that it's already balanced, I do not necessarily write out the entire formula. And for those of you who looked ahead, you can see that in both of these cases, like on your own 10.4, we have 1, 2, 3 reactants and 1, 2, 3, 4 products. Okay. Now, if you read the problem, it says if 200 milliliters of 0.75 molar hydrogen peroxide is reacted with an excess of all the other reactants, how many grams of oxygen will be produced? In this reaction equation, what are the only two molecules I really care about? I'm assuming I'm only going to care about the hydrogen peroxide and the oxygen, right? So, if I'm working this just for myself, I'm not turning it in for grade or anything like that, if I'm just working out for myself, I might very well write the reaction as, like for example in 10.4, it's 5 hydrogen peroxide plus a bunch of other stuff. Reacts to produce 5 oxygens and other stuff. And I have no intention on filling in the blanks. Why? Because if it's balanced, I don't care. If I'm doing the stoichiometry, all I'm doing is relating. In the end, all I'm going to actually relate is my hydrogen peroxide and my oxygen. You see that? Because it says, if I have 200 milliliters of a 0.750 molar hydrogen peroxide solution, and it reacts with excess of everything else, how many grams of oxygen will be produced? So if I've written everything out, I still wouldn't use it if it's balanced. If it's not balanced, I need to write it all out and then balance it so I can use stoichiometry. But stoichiometry here is going to tell me it's a 5 to 5 or a 1 to 1 relationship, so the multiple is going to be 1. So again, I'm moving here from lower left to upper right. It's going to be multiply in this direction to get this. It's going to be multiplied by 1 to get this. And then it's going to be multiplied by the molar mass of oxygen. Now some of you still want to go in here and say, what's my mass going to be? What is the mass of an oxygen? Okay, what is the mass of an O2 molecule? Okay, what is the mass of 5 of them? That's not what we're doing here. What is the mass of 1 mole of O2? So it's 16 grams per mole for one oxygen, 32 grams per mole for an O2 molecule. The fact that it has a 5 up there, that's accounted for in the stoichiometry. That's accounted for in the 5 to 5. Okay? So we're going to multiply this by is the molar mass of 1 the mass of 1 mole of that molecule. The mass of 1 mole of that molecule is 32 grams per mole. And that's why in this movement, 0.2 times 0.750 is going to give us 0.15. See? Yeah. 0.150. It's a one-to-one relationship with how many moles are going to be produced. If I have 0.150 moles of hydrogen peroxide, that's what H2O2 is. 0.150 moles of hydrogen peroxide that react, then how many moles of O2 are going to be produced? Same number of moles, 1 to 1. Okay? You can. So 0.150 moles of O2 are produced. Each mole has a mass of 32 grams. So I'm going to multiply up, and it's going to come out to be 4.8 grams. At a certain point, once you learn the diagram and how to plug in the information, whether you're going from product to reactant to product, or comparing in titration, comparing two reactants, it doesn't really matter. If you have comfort with the pathway and know where to place the information you're given and how to walk the steps to get there. Like the last module, there are 2 or 3 different subsections presenting different iterations of the same thing, but once you have the process diagram down, you're comfortable moving throughout the equation. And you see how we don't really care about the other molecules and reactions in the products unless we have to balance it. Pen 5, it talks about purifying. In this one, you just have to really think through, because they're going to give you some information that really isn't directly usable. You kind of have to make some inferences. You kind of have to conceptualize it just a bit. So let's walk through this one together. It says one way to purify a mixture of 2 metals is to add to the mixture something that reacts with only one of the metals and turns it into an aqueous compound. You've got 2 metals. You add something to it that basically dissolves the other metal, goes into solution, and you're left with the second metal that doesn't go into solution. The mixture can then be filtered, isolating the other metal. So if you got 2 metals, one of them goes into solution, and you pour it through a filter, whatever did not go into solution is left in the filter. That's what they're saying. A mixture of magnesium and aluminum was treated in such a way as to isolate magnesium. So if you're isolating magnesium, then the aluminum must go into solution. Sodium hydroxide, which reacts only with aluminum, was added. So since that sodium hydroxide reacts with aluminum, it's going to put aluminum in solution, and it'll be basically pour it through the filter. It'll go through the filter. What doesn't go into solution will be left behind. Now, even if you didn't get all that, you see the reaction equation given to you right there. So the aluminum was converted to an aqueous salt. A salt being an ionic compound, right? It's an aqueous compound, which means the ions are broken up, but they're in the solution, and when poured through the filter, they go through the filter. And the magnesium was not part of the reaction, and it stayed as a solid. The solution was then filtered, isolating pure magnesium. Now, here's where we get to the actual problem. That's all concept to that point. It says, if a mixture of these 2 metals contained, it gives you a mass of aluminum, then how many liters of the sodium hydroxide solution would be needed? There's the core problem. So you have the reaction equation and the core problem below. Now, using the same kind of thinking as before, we have a balanced reaction equation there. What are the only 2 molecules I'm actually concerned about? molecules or atoms, elements? Which ones? I'm only concerned about aluminum and the sodium hydroxide. Okay? Because it's in the bottom there, it says, if I have this mixture and 1.5 kilograms of aluminum with 1.5 kilograms of aluminum, how many liters of sodium hydroxide solution would be needed? So in this I'm relating aluminum and sodium hydroxide. So from the reaction equation, 2 aluminum and 2 sodium hydroxides react to produce. And frankly, from my notes, when I'm working on it on my own, it's all I really need. The rest of the stuff happens for concept, but this is going to be part of my solution pathway, these 2 molecules. So I've been given 1.5 kilograms of aluminum. It says how many liters of a 8.1 molar sodium hydroxide. So how many liters of a 8.10 molar sodium hydroxide do I need? This mass, how many liters of this molarity of this do I need to balance that out? So you see that it's a 2 to 2, which means the multiple is 1, either way. So hopefully you see that this is my starting point, and that this is my ending point. I'm going to be moving in that direction. Hopefully from reading the problem, you can see how to set up the solution pathway. And then we just have to walk it. What would we do? We have 1.5 kilograms. What do I need, or what do I do next? Okay, you want to change it into grams? We can do that right here, and we'll make that 1,500 grams. It's actually here, okay? It's not the sodium hydroxide, it's there. Okay, next step. We're going to divide by the molar mass of the aluminum. Okay? That's going to give us a certain number of moles. It's 27 grams per mole. And dividing by that gives us 55.5 or 55.6 moles of aluminum. When we have 1.5 kilograms of aluminum, we have 55.6 moles of aluminum. They relate 1 to 1 in reaction. So how many moles of sodium hydroxide do we need to react with? 55.6 moles of aluminum. And then to figure out the number of liters, we divide the moles by the molarity. .86. Should look very familiar. We haven't introduced anything new today, other than I think it's really here just for a refresher from last module to get us ready for whatever may be coming. Insert evil laugh. No. Part of going back to this molarity issue is because the next section is on molality. Remember we talked about this? We went over molarity, but you're going to have to learn another term called molality. And it's not the same as molarity. I know, hopefully you've already read the section. And, we started off this module with 3 days of just study hall. So if we took advantage of those 2.5 hours for reading and outlining and things like that. So molality we get into next, and it's not based upon the number of moles per liter, but it's based upon the number of moles per kilogram of solvent. So you can see I'll be very dependent upon the solvent. right, of how many moles of solvent you have, because it's based on the mass, not the number of moles of solvent, or the volume of solvent. It's based upon the mass. So it's slightly different than molarity. Any questions for me before you take the next 10 minutes or so, maybe start working on practice problems 3 through 4, 5, I think is the homework. Okay. It's not terribly difficult. But feel free to go ahead. Any questions? I'll take them. And these are homework. If you do the shortcut, I'll allow you to do that on your homework. Okay, but make sure that you can actually do it. Make sure you don't need any other information. If you're just concerned and it's better for you to make sure you see the whole equation no matter what, it's worth it to take the extra minute or so to write it all out. Okay, until you're comfortable.